is it going to, this is mechanics, so it's going to be not a density, but it's just going to be the Hamiltonian. Okay, so this is P mu x mu dot minus L, and L I can write density also. What is this? What am I doing? I think I will think about it and then tell you what I'm confusing. So I was just wondering about the densities and the full quantities. Okay, supposing I have canonical Hamiltonian density P mu x mu dot minus L, and this is what I would have. So MC times P mu, I have erased. What is P mu? Is MC x mu dot divided by minus x dot square times x mu dot minus of minus MC times minus x dot square. So if you calculate MC by square root of minus x square, then you have x dot square plus and this turns out to be identically 0. So this guy is identically 0, and therefore one again this is only a manifestation of the fact that it's a severely constrained system. In fact, all string theory, actually even gravity theory, is a severely constrained system. Severely constrained means you have huge number of constraints in the theory. In the gravity theory, if you analyze it, the constraint structure of the theory, then this is what you would obtain. Okay, in electrodynamics, for example, it's constrained, but not as severely constrained as string theory or gravity theory is. Okay, so here, I mean, in electrodynamics, for example, H canonical does not vanish identically. You still have something. Okay, but here even the canonical Hamiltonian vanishes completely, and then using the Dirac procedure, so the correct way to handle a theory is to construct a total Hamiltonian, which is canonical Hamiltonian plus you add up the constraint in the theory with the help of the Lagrange multiplier field. Okay, so this lambda is a Lagrange multiplier field, and you add up this constraint into the canonical Hamiltonian, and this gives the total Hamiltonian. And the dynamics of the theory is then determined not by the canonical Hamiltonian in general for all constraint systems, but by the total Hamiltonian. And for unconstrained systems, these two are identically the same. So let me give you an example of the unconstrained system. For example, just go to field theory. Always, I like to go back to simple field theories for my understanding purposes. So scalar field theory. You write 1/2 of d mu phi minus 1/2 of m square phi square. Here, when I obtain P, this is del L over del phi dot, you can see that this is del L over del phi dot of the first term, 1/2 d0 phi, all other terms would give me 0. Okay, the time derivatives, d0 phi, this is phi dot square. So this gives me 1/2 into del over del phi dot of phi dot square. So this is 1/2 into 2 phi dot. Okay. So this is an example, this is the best example of an unconstrained system. Okay. here, when you obtain the canonical momentas of the theory, then you find that some of them, here P is depending on phi dot. Phi dot is velocity. So as long as a P depends on a velocity, any of the velocities of the theory, supposing I have phi 1, phi 2, phi 3, phi k, different fields, and if I have different kinetic energy terms for the theory, okay, then there may be some P's which would not depend on any of the phi dots. Okay, they would correspond to the Dirac primary constraints, and that would be constraint system. Here, the common. So here P is equal to phi dot, and so it involves a velocity. So P involves a velocity, and therefore there is no constraint in the language of Mr. Dirac. Okay, so it's an unconstrained system. It's another side remark that eventually one could interpret this kind of a system as so you see, and all gauge invariant theories, it's a very landmark thing actually. All gauge invariant theories, they have to be constraint systems, and their constraints must somehow form a set of first class constraints only. Then it's a gauge invariant theory. Otherwise, it's a gauge non-invariant theories. And from gauge invariant theories, one can construct gauge non-invariant theories by going to the gauge fixing procedure. So you fix the gauge. You might recollect that in electrodynamics, when you quantize the theory, you invoke some of the other gauge fixing condition or gauge conditions, as you call it. So therefore, by construction, by definition, this theory just cannot be a gauge invariant theory. It's an unconstrained system. Or one could interpret that the gauge non-invariant system could somehow be thought of as a fixed gauge invariant theory. But let us not go into that. But I just wanted to remind that in string theory, in all kind of actions, not to talk of point particles, even if you go to one-dimensional strings or membranes or whatever, these are all severely constrained systems. We should have a little bit of idea about how it goes, okay? And in particular, when the people talk about the Virasoro constant, we should always remind ourselves that they are really obtained from the Dirac's theory, and they are Dirac constraints, but because they satisfy a particular algebra, which is called the Virasoro algebra, they are also referred to as the Virasoro constraints of the theory. So I think I could remove this all. Have I given you some flavor of this? Yes, we can always go back to it. Usha and myself, we have spent sufficient time on this constraint quantization process, because actually one cannot really obtain quantization, even in the, not to talk of string theory, even for field theories, one cannot do quantization without knowing the constraint dynamics and without knowing the constraint quantization of the theory, whether it's Hamiltonian, whether it's path integral, whether it's BRST quantization, everywhere you need those kind of procedures. Okay, so now here we discover that for this Nambu-Goto action for the relativistic point particle, we find the mass cell condition, which is actually this constraint, and this when added to HC, it gives us HT, the total Hamiltonian, and this describes the dynamics of the particle. Okay, so because we have another 10 minutes time, could I go on for another 10 minutes? Yes, very good. So we could do a little bit further. Okay, so that the pages that I took out may be covered, and this would be a logical end to one kind of a description. Then we could go over to something different next time. This time, sometimes you can always control me and check me, but because I have in my mind that the second half of the semester I want to spend on superstrings. Okay, so for that I would like to spare time, and therefore here we might do most essential things. Okay, somewhere I might cut short on the stories, Okay, but or else we will have to invent one or two or some extra lectures sometimes, not always, but once in a while, or maybe towards the end when you find, so that a few things that I have somewhere in my mind, I may better be able to tell you. That's the best thing, you see. The purpose of a teacher, as I consider it, that I should be successful in transferring some knowledge to you, so that at the end of the day, you do not think that you wasted your time listening to me. Okay, you should have the feeling that you did learn something. Okay, so that would be my success of my teaching. Yes, so now here, as we have seen in this action that we have written a couple of times, that the path is being parameterized by time tau. Okay. So on the word line, so the path is being parameterized by tau, and because the action, if all of us compute the action sitting in this room or sitting in some spacecraft or somewhere in all frames, the action has to remain a Lorentz scalar or Lorentz invariant. So this means that observer can reparameterize